Hello, thank you for inviting me to give this keynote lecture at the International Symposium on Advanced Engineering Technologies. I'm honored to give a presentation about open source GIS software and tools for hydrology. So my name is Hans van der Kwast. I'm a physical geographer by background, and I work at IHE Delft Institute for Water Education. I'm an advocate of open source software for GIS, and I am a co-author of the book QGIS for Hydrological Applications that I wrote together with Kurt Menke. Recently, our second edition of this book came out with a lot of new tools included. You can easily find me on social media, and I have my own YouTube channel. I will tell more about it later. So I work for IHE Delft Institute for Water Education, which is the largest international graduate education institute in the field of water. And many of our students, who come from the global south mostly, learn GIS through open source software such as QGIS. Let's start with the history of GIS. Before the 60s, we were in the dark ages because there were no computers available to do GIS. Between the 1960s and 1975, there was a lot of pioneering going on, and the first GIS systems started to exist, but still not many people could use that. Between 1975 and 1990, the commercialization of GIS software took place, which resulted in licensed software products. And this was also the time when the most popular GIS software started to get used. Then we got the proliferation of users between 1990 and 2010 because computers became cheaper and more people got educated in commercial GIS software, such as in master programs at universities. But nowadays we have the open source explosion, where we have access to many different tools that are freely accessible and can be downloaded from the internet without any restriction. And we are free to use and reuse, but also to contribute to the software. And QGIS is a great example of GIS desktop software that even integrates other desktop tools like GDAL, GRASS. You see here in the animation a whole list of tools that you can use. PC Raster, which is a nice toolbox for map algebra, which you can also use for spatial dynamic modeling. Saga, you see it comes with many different tools, and a few are very important for hydrological analysis. And there's also Whitebox tools, for example, which also has a great set of tools for hydrological analysis. And QGIS can give you access to all these tools from a third party. We call that processing provider plugins. In the paper for this symposium, I give a review of using these tools for stream and catchment delineation. And unlike using a commercial package, you have then the possibility to use different algorithms which suit better your purposes instead of being stuck with one set of tools that might not work in your case. In the procedure for stream and catchment delineation, you first acquire a digital elevation model. Then that normally comes in tiles that you need to mosaic. Then you need to reproject the DEM, make it smaller because the tiles cover a larger area than you need. And you don't want to work with too large areas, otherwise you get computational issues. You need to interpolate the voids, which are no data cells in your DEM. And to make it hydrologically correct, you need to fill the sinks. Then you can derive the streams, define the outlet, and delineate the catchment. This whole procedure is generic and can be done with commercial and open source tools. And within the open source landscape, you can use many different algorithms to achieve the same result. But some algorithms will be more robust or work better in certain situations, or have many more arguments that you can change. Open source software also connects well to open data. And you can use plugins to download this data directly into QGIS, for example. There is the Open Topography DEM Downloader plugin, which can download 8 different DEMs. And you need to, as a researcher, look for the one that is suitable for your application. There's also the SRTM Downloader plugin, which downloads the DEM tiles from the Shuttle Radar Topography mission for the area that you've defined in the map canvas. Another example is to delineate the streams in the whole procedure, and you can use different methods like using Strahler orders, which you can calculate with Saga, with PC Raster, And then you can calibrate the Strahler orders with the reference layer to find out from which order or larger you call it a river. Another way of doing it is using the flow accumulation. You can also do that with Saga, PC Raster, or GRASS. And then you need to use the reference to find the accumulation threshold from which you call the accumulation a river. As a researcher, you also have a lot of choice if you use open source software. For example, you can use the classic D8 algorithm, which looks in 8 different directions in a moving window to determine the flow direction or the slope. But there are also other algorithms like the multiple flow direction, which looks in a larger area and can have more continuous definition of the direction. And there's D infinity, which uses a tessellation to find the flow direction. Also for filling the sinks, we can use the Wang and Liu algorithm, which comes with Saga, or we can use the one from PC Raster, for example, which has many arguments that we can tune, so we can adjust the algorithm to what works best for our study area. You can see in this picture the different variables in the tool that we can change. Because these tools are available in QGIS, you can also use them in the graphical modeler, and you can make 3D visualizations, which help you with the processing and interpretation. Here you see an example for catchment delineation in the graphical modeler of QGIS, and it uses GDAL tools in combination with Saga tools. So with open source, you cannot just use the software, but you can also contribute to the development, and you can work together with other developers and researchers to improve software, create new tools, or create your own plugin. And we normally do that in a Hackfest. Nowadays, we call that a contributor meeting because you can contribute in many different ways than just coding. Maybe you want to write documentation or work on translations. The next contributor meeting is a side event of the FOSS4G conference in Firenze in August. And FOSS4G stands for Free and Open Source Software for Geoinformation. And that's the place to be to learn more about open source software. I will give there a workshop on using the PC Raster tools in QGIS and in Python. And this is an example of what I have developed in collaboration with others during such a Hackfest. And here you see a tool that we developed to visualize flow direction using arrows on a map. And that also works in 3D, as you can see in the animation. So here you see how it works. After exporting it to a mesh format, we can change the styling of the mesh data. And we can choose to not show the contours, but to show the arrows. And with a few changes in the settings, we can see that we visualize flow direction nicely with arrows, which makes it much easier to interpret by researchers. Another tool that we developed was to create multiple catchments from a layer with outlet points, point layer, and then we can save the result in a geo package, and we will have all the subcatchments as vectors. Here you see it running, and we can easily program this in Python because QGIS supports Python, and when we have those other packages available, we can write new tools. And after writing tools, we can also easily share it using the QGIS resource sharing plugin. Here you see that we can connect to a Git repository and that I can download models and scripts. So here I install the scripts and I get 9 scripts. And here I install the models. And these will be added to the processing toolbox. So if I expand the model section, I will find here the models that were shared through the resource sharing plugin. And I can simply open the tool dialog and fill it in to calculate all the subcatchments, or I can edit the graphical model and adjust it to my own needs. So here you see the catchment delineation for subcatchments using PC Raster tools. You can also write scripts in Python, and It's quite convenient to write your tools in that way because it creates these nice dialogues, and they are more efficient than using the graphical modeler. In this way, you can calculate, for example, the topographic wetness index and create a tool with a dialog so other people can use the same workflow. There are also many useful plugins, like the WaterNet analyzer, which analyzes the flow network. And if you click on a point in the river, it will show you where it will go to the outlet, so which tributaries it will follow. Open source software is now also very powerful for visualization of hydraulic information, like you see here in the mesh visualization of QGIS, which also can be used in 3D and animated in time. There are also tools that are based on QGIS and are open source, but are made specifically for the purpose of hydrological and hydraulic analysis. One of those tools is Lekan, where you can quickly derive a catchment and calculate different hydrological parameters, like unit hydrograph, using different methods. The advantage is that it's easy to use. The disadvantage is that you use a lot of presets from the dialog. Well, if you have QGIS, you can use many combinations of other tools. And then in the end, what is also very powerful is the visualization of hydrological data with open source GIS. There are all the time more functionalities released that are very useful for improving map design and also to do visualization of flow networks. If you want to learn more about open source software for hydrological and other applications, have a look at gisopencourseware.org. It is a website that I moderate where you can find a lot of different courses for free. It comes without support and without a certificate, but you can find a lot of nice courses with videos, and they are translated in some other languages by volunteers. So if you would like to see a course in Turkish, then you can contact me and I can give you access and you can help me with the translations. You can also go to my YouTube channel to find a lot of videos, especially about GIS for hydrological applications using open source. And finally, you can also have a look at the second edition of the book QGIS for hydrological applications, which was just released. And this will guide you through all kinds of workflows that are important for hydrologists. And by purchasing the book, you support IHE Delft students from the Global South to join QGIS and Phos4G events. And this is important because these communities lack a lot of participants from the Global South, and a lot of participants are male and lack female. So in conclusion, many open source tools are available for hydrological applications, and these tools are developed by communities, and you can even be part of these communities and contribute yourself to the tool sets. These tools have advantages and disadvantages, but the great thing is that you have a choice of different algorithms and you can decide which algorithms are fit for your purpose, and you can test different algorithms and their results. So scientifically it is a big advantage, and you can also peer review the algorithms. So although many people and especially educators have been trained in commercial software, I hope that this will be changing and more students will be also educated in using open source software and learn also how to contribute to it by learning programming languages and working together using GitHub repositories. And in this way, science can progress much faster than being dependent on commercial software with expensive licenses. So with this, I would like to end the presentation.